Okay, logarithmic differentiation is a trick that we use to take derivatives of stuff we otherwise wouldn't know how to do derivatives of, or to make really hard problems slightly easier. Okay. And the trick is we're using implicit differentiation. The key to this is to remember that if you have a y and you take the natural log of it, and then you take the derivative of that, this is implicit differentiation. The derivative of natural log of anything is 1 over that thing times the derivative of what's inside. What's the derivative of y? Y prime. This is the key. The derivative of natural log of y is 1 over y times y prime. We're using implicit differentiation to do the logarithmic differentiation. Okay, and we're just going to do a bunch of examples. Okay, so here I've got y equals some function raised to a function that has x's in it. This is when you know you need logarithmic differentiation. I cannot use power rule here. Power rule only works when your exponent is a number. Tangent of x is not a number. So I'm going to use logarithmic differentiation. That's an N right there. So to do that, we take the natural log of both sides. I'll write out the steps here. I'm allowed to do that. The log is a 1-to-1 function. As long as I'm in the domain of log, we're okay. So we get the natural log of y equals the natural log of the right side. Oops. So this is what I'm taking the log of over here. Now you got to remember rules of logs. The entire point of taking the log of both sides is to use rules of logs. So maybe let's write down all of our rules of logs, just as a refresher for everyone. There's 6 of them. Log base b of b equals 1. A log is a question. What exponent do you put on the base in order to get whatever's inside? So the reason this is true is because b raised to the b power, or b raised to the 1 equals b. B raised to that power equals what's inside. Rule number 2, log base anything of 1 equals 0. And the reason for that is because the base raised to that exponent equals what's inside. B to the 0 power equals 1. Rule 3, log any base of b to the x. The log and the exponential function are inverses of each other. You just get x. So the reason for that is because b to the x is b to the x. B raised to that power equals what's inside. This should be a refresher, everything we're going through here. Then you have your sum rule. Log base b of multiplied inside becomes added outside. You have your quotient difference rule. Divided inside becomes subtracted outside. And then you have your power rule for logs. Log base b of m raised to the n, that exponent there can come down to ground level with everyone else. These I won't prove, but they really just come from rules of exponents. You got to know the rules of logs or you're going to have a really bad time here. So that's our first step here. That's the entire reason that we're taking the log of both sides is to use this rule right here that says that tangent can now come down to ground level. So that tangent came down. I have not done any calculus yet. I took the log of both sides so that I could get that x, my independent variable, out of the exponent. Otherwise, we don't know how to take the derivative. Now, we take the derivative with respect to x of both sides. Here's the key. This is what makes logarithmic differentiation work. The derivative of natural log of anything is 1 over that thing times the derivative of what's inside. The derivative of y is y prime. Okay, on the other side, I've got a product of functions. There's one, there's a second. I have to use product rule. Derivative of secant of, the derivative of tangent of x is secant squared of x. Times, leave the second one alone, plus derivative of the second. Derivative of natural log of anything is 1 over that thing times the derivative of whatever is inside. His derivative would be 8x to the third plus 0 times the first. So product rule, derivative of the first times the second plus derivative of the second times the first. Okay, I'm almost done with it. Nobody asked me for y prime over y. I want y prime. So y prime would be y times all of that stuff, all that in here. But I know what y is. That's my original function. It's right there. So then we would get y prime equals all of that. That's y right there. I keep forgetting what it was. Times all this stuff. And then this fraction here, I'm just going to write that like more fraction-y. 8x cubed tangent of x over 2x to the fourth plus 1. And I need my bracket there. That is the derivative. And the only way we could have gotten that is a logarithmic differentiation. Okay, let's do another one. Now here, I don't have a function raised to an exponential function that has a log in it or has my x in it. This one I could just do using quotient rule and a whole bunch of product rule, but I'm going to show you a trick here. So I don't have to use logarithmic differentiation on this, but if I do, it simplifies stuff so much. Watch what happens. If I take the log of both sides, I'm allowed to do that. This guy here, I'm going to write that square root. I'm going to write that as 2x plus 1 to the 1/2 power. It's going to clean things up a little bit later. Now I can use rules of logs to split all this up. So we get ln of y equals. Anybody on the top is going to have a plus in front of them. Anybody on the bottom is going to have a negative. So this is just going to be, and you can check these details on your own. I haven't done any calculus yet. Anybody on top is a positive, anybody on the bottom is a negative. And this is, here, I just want to make sure that's clear. That's log of sine cubed of x. Now, any of the exponents can come down. This 1/2 can come out front. This I could just simplify, might as well. Natural log of e to the x, those are inverse functions. They just cancel out, leaving behind just x. This 3 I could bring down. Now, take the derivative. Now it's the first time I'm doing any calculus. That was all just algebra. Let's do some calculus. Take the derivative with respect to x, because that's my independent variable of both sides of everything. The derivative of natural log of anything is 1 over that thing times the derivative of what's inside. The derivative of y with respect to x is y prime. Derivative of ln of x is 1 over x. Derivative of this 1/2 is going to come along for the ride. Derivative of ln of junk is 1 over junk times the derivative of what's inside. The derivative of that is 2, which is going to end up canceling that 1/2 there. That's just a coincidence. That won't always happen. Derivative of minus x is -1. -3 comes along for the ride. Derivative of log of sine is 1 over sine times the derivative of the inside. Derivative of sine is cosine. Okay. So now I'm going to clean this up a little bit. What do we got here? We got a 1 over x. Those canceled, so I just get a 1 over 2x plus 1 minus a 1, and then -3. That's cotangent of x. Now, nobody asked me for 1 over y prime. I want y prime. So multiply this y over to the other side. So all of that is going to go in here. I'm just being lazy. I don't feel like writing it. What was y? All this stuff. I already forgot what it was. X cubed, or 3 e to the x sine cubed of x times all of this. Plus 1 minus 1 minus 3 cotangent of x. So that's the derivative. Now we would get the same answer. It might not look as pretty. We would get the same answer though if we use quotient rule and a whole bunch of product rules and a little bit of chain rules and so forth. Okay, let's stop here and then we'll do more examples.